Okay, in this one, I want to use the Fourier series for the absolute value of t, which we wrote down, to compute the sum from n equals 1 to infinity of 1 over n squared. I think I can do this. We'll see. I don't know. Maybe a little bit scared, but we'll see. So the Basel problem is about the sum from n equals 1 to infinity of 1 over n squared. Okay. What I'm going to do is I'm going to organize the terms of that sum into two groups. One corresponding to even values of n and one corresponding to odd values of n. So here are the odd values of n. The terms corresponding to the odd values of n. Oh my god. Wait. This is funny. And this is the truth, okay? I'm no good at arithmetic, okay? Do you notice that I completely skipped over n equal to 4 in this series here? I wish I could say this was your. You know what? I do wish it. I wish it was your fault. So let's just make that dream a reality. This is somehow your fault. Good. That makes me feel better about myself, and that's really what counts here, right? I forgot. Sorry, you didn't catch. Somehow you allowed me to forget the n equal to 4 term, and it's your fault. Yeah. So I want to think about the odd terms and the even terms. The odd terms are corresponding to odd values of n. It's going to be n equal to 1, n equal to 3, n equal to 5. And it keeps going, of course. And then the even terms. That's the n equal to 2, n equal to 4, n equal to 6 terms. That's 4. Yes, here we go. All right. Now, what I'm claiming, okay, is that this computation here gives us a handle on the sum of the red guys, of the odd ones. Because do you see how there are these odd squares of integers appearing in the coefficients of, after all, this is a sum, infinite sum over n odd of terms like this. All right? So I think that's going to give us some foothold to understanding what's happening when n is odd. What we need to do is understand what happens when n is even. Okay? I want to understand the sum from n equals 1 to infinity of 1 over n squared, but only thinking about the even terms, the even values of n. Okay, so here's what I'm going to do. Here's my funny move. Is it funny? Well, I'm not sure. I'm going to call the solution. I'm going to call the value of this infinite sum here. I'm going to give it a name. I'm going to call it L. No, let's call it B for Basel. So that's all the terms. But how can I get just the even terms? Well, what if I was to just double n? So let's think about the sum over just the even terms. So what if I was to take the sum from n equals 1 to infinity of 1 over, now 2n whole thing squared? Think about what this is. This is when n is equal to 1, 1/4. When n is equal to 2, this is 1. When n is equal to 2, this is 1/16. When n is equal to 3, this is 1 over 36. In other words, it's exactly the blue terms that we've got in the full Basel problem, right? On the other hand, notice that this is equal to, but just by looking at the thing that we're summing up, this is the sum from n equals 1 to infinity of 1 over 4n. I'm just squaring the 2 and squaring, and squaring the n. So I get 1/4 1 over 4n squared. So I can pull out the 1/4. This is equal to 1/4 times the sum from n equals 1 to infinity of 1 over n squared. But what the heck? That's 1/4 b. Do you see? Because b, as I defined it, is the sum from n equals 1 to infinity of 1 over n squared. There's the sum from n equals 1 to infinity of 1 over n squared. So that when I sum over just the even ones, just the even ends, I get 1/4 of b. Okay, all right. So what? Who cares? Well, I don't know. I guess I care a little bit. Why? Well, that's a good relationship. Now I should actually think about the odd ones, okay? And for that, I'm going to use this absolute value of t guy here. Let me think about that now, okay? You're just bear with me here. What I'm going to do is plug in t equal to 0 into both sides of that Fourier series for the absolute value of t that you see at the top here. So plug in t equals 0. So on the one hand, we get 0 because the absolute value of 0 is 0. Did you know that? It's true. What happens when we plug in t equals 0 into the series? We get 1/2 minus 4 over pi squared times cosine of 0, which is 1, minus 4 over 9 pi squared times 0, times cosine of 0, which is 1, minus 4 over 25 pi squared times 1, etc. So we get here 1/2, and I'm going to factor out a 4 over pi squared times 1 minus 1/9, and that's a negative. No, I'm sorry. I factored out a negative. So it's plus 1 over 25 plus 1 over 36, etc. Great. Yes. Now what am I going to do? Now I'm going to subtract 1/2 from both sides of this equation. And then I'm going to multiply both sides by negative pi squared over 4. So I get that pi squared over 8 is equal to 1 plus 1/9 plus 1/25 plus all the way out. In other words, the sum, these red guys here all add up to pi squared over 8. I think this is it. Because b is the sum of all the odd terms with the sum of all the even terms. The sum of all the odd terms now we know is pi squared over 8. The sum of all the even terms is 1/4 b. So I'm pretty sure we win. In other words, what we now know is that b is equal to pi squared over 8. That's the sum of the odd terms plus 1/4 b. And now this is like, an 8th grade algebra problem. Solve for b. Subtract b, 1/4 b from both sides. And then multiply both sides by 4/3. And I think that's pi squared over 6, which is the famous result for the Basel problem. Now, I don't think Euler solved it this way, but we got lucky because the Fourier series for the absolute value of t just so happened to involve the reciprocals of the squares of the odd integers. And with this little trick involving the reciprocals of the even integers, we were able to kill the Basel problem. Good job to us. can pat ourselves on the back, feel good about ourselves. And yeah, great. Okay, that's it for this set of videos. So long. Goodbye. Farewell.